this is just a little demonstration to illustrate an important principle of statics, which carries over into dynamics. So here I have a couple of wooden blocks, and what I'm going to do is just push on the top block, and as you can see, it drags the bottom block along with it. You could probably guess that I could push hard enough on the top, and it would probably push it over the top, which indeed it does. And I can do that, but in the meantime you can see that the bottom block still does move on the table. So let's draw a free body diagram of what's going on with the bottom block. The bottom block has this force of friction that actually moves it forward. And there's a force of friction at the bottom where the interfaces with the table as well. There's a normal force, a weight. And where does this force of friction come from? Well, it comes from the top block. The force of friction, because it's moving, is mu normal, and I'll just put this, there's going to be a normal force here and a normal force there. So in other words, the interacting forces, the normal forces have to transfer equal opposite between the blocks. The force of friction is also transferred equal opposite between the blocks. This force of friction here causes this to have a mass times acceleration, and well, I've got the pushing force, which is on the top, and so the sum of these two forces causes this to have mass times acceleration. All right, so the next thing I want to do is illustrate what happens if I push on the bottom block. All right, so again, the same thing might happen. I'll push on the bottom block, and you can see the top block obviously follows along with it, which makes sense. And how does the bottom block move? Well, there's a force of friction between the two that actually brings the top block along with it. But you can also expect that if I push slowly, it goes slowly. You can also expect that if I push it kind of rapidly, the top block would actually fall over backwards onto the table. So let's draw a free body diagram of that. What's going on here is I'm pushing here with a force P. There's clearly a force of friction at the bottom. And there's a normal force that's made here. And what's going on with this is what makes the top block move forward is the force of friction between the two, which then goes equal opposite on the bottom block. Oops, that's the force of friction of A. So again, in both cases, the normal force transfers equal opposite, and the force of friction transfers equal opposite. And what makes these things go is the sum of these forces will have a mass times acceleration, and that force will cause this to have a mass times acceleration. Okay. Now that we've watched that demo, I'd like to go through this problem with you. And here we have a couple of blocks. The top block weighs 20 pounds, the bottom block weighs 50 pounds, and we're going to push the top block with a force. We're going to call it force P. And for this particular problem, there is no friction at the bottom. However, there is friction between the blocks. So you can guess what would happen is that if I push gently enough, they would travel together as a system with a single mass times acceleration. However, if I push hard, if I pushed with a hard enough force or a great enough force, the chances of, I might not be able to push it hard enough so that the A slides over the front of the bottom block and it goes that way. B, however, still moves that way due to this force. So the first question to ask is how, with a force of 6 pounds, which is right there, is it enough to shove it over the top? In other words, does A slip relative to B? Well, one way to find out if it doesn't slip is to find out or to analyze the slipping conditions. And at slip, the force of friction between the two blocks is the maximum, which is going to be mu normal, which is mu mg, which is 8 pounds. Now for this problem, I'm only going to be using the static coefficient of friction. I'm not going to use the kinetic coefficient of friction right now. So we can see that because the pushing force of 6, we're drawing the free body diagram of the top block then. Here we have the block, we have a weight, we have a pushing force, we have a normal force, and we have a force of friction which is going to resist that motion or be going backwards. If the pushing force of 6 does not exceed the friction force, then there is no slip. And so that's pretty easy to see that because 6 is less than 8, we know that there is no slip between the two, and so that they do not slip because you don't have enough force there. All right. So So if you conclude then that the two blocks travel together, you can find out the total you can find out the acceleration by just drawing a single free body diagram for both blocks together. You're pushing with a force of 6. You have a total mg coming down, a total normal force. In this case, the force of friction at the bottom is equal to 0 because there is no friction at the bottom. And you can see that the sum of the forces in the x is mass times acceleration in the x. The only forces I have in the x direction, positive, is going to be that pushing force, and I can solve for the acceleration of 2.76. Now, how much is the friction force, however? There is still a friction force, and we can resolve that by drawing a free body diagram of either the top block or the bottom block. Either one works, but let's look at the top block first. So I'm pushing with a force of 6. I have a weight of 20. There's a normal force and this force of friction. I know the acceleration because they travel all together. So all I have to do is sum of the forces in the x is mass times acceleration in the x, and I can solve for that force of friction right there. And it is 4.286. I could also draw off a free body diagram of the bottom block. And here we have 50 pounds. There's going to be a normal force here. There's a force of friction if there was any friction at the bottom, which there isn't. It's smooth on the bottom, so this force of friction is 0. But the only thing that's pushing the bottom block forward is that mating force of friction right there. The force of friction between the two blocks. I know the acceleration because they travel together. It's the same acceleration for both. So all I have to do is sum of the forces in the x. The only force that I have in the x direction is that force of friction, and I can solve for the force of friction of 4.286. And I get the same answer. We expect that, but it's comforting to see that. Now, what if I increase that force? Instead of making it 6 pounds, let's bump it up to 10. If I push with a force of 10 pounds, I know that the force of friction is still, or the force of friction maximum is still 8. So that if I bump it up to 10, push it with a force of 10, I think you would expect that it might slip. So let's see if it does. Let's assume slip, and let's draw our free body diagram of the top block right here. I'm pushing now with a force of 10 pounds. Got a mg, or a weight of 20. I got a normal force, force of friction going backwards. And that results in a mass times acceleration. So if I assume slip, we've already solved for the maximum force of friction is 8 pounds. And let's just plug that into the free body, or into the equation of motion. 10 minus the force of friction is, here I'm only using the mass of the top block of 20 pounds, and I can solve for that acceleration of 3.22. Let's just confirm that that's a good number. Let's draw the free body diagram of the bottom block. All right, the bottom block, what's pulling it forward is going to be that force of friction, which is transferred equal opposite from the top. I've got a normal force transferred equal opposite from the top. It has its own weight. It's got a normal force. Again, the force of friction at the bottom is 0 because we have no friction at the bottom. But if I say that that force of friction at the between the two is 8, is sum of the forces in the 8 or in the x is mass times acceleration, and I get the force of friction at the bottom is 5.52. Now, I got two answers that are real answers, and you would think that that might be correct. However, look at the magnitude. There's no way, really, that the acceleration of the top would be less than the acceleration of the bottom. Or in other words, there's no way for the bottom block to have a greater acceleration than the top block. So what we've discovered here is that this is not a good answer. It's not a good assumption. They actually don't slip together because that cannot be true. You cannot have the acceleration of B greater than the acceleration of A. So that's a bad assumption. It is not slipping, even though I'm pushing with a force greater than the actual friction force because of this, because it's a, if it was a statics problem, you could conclude that it was slipping. But since this is a dynamics problem, we have to take the whole equation into account, and we can see that it is not slipping. All right, so then how much force does it make, or does it take to make it to make it slip? So let's figure that out. We're going to again draw separate free body diagrams of the two blocks, and let's do this one. For slip to occur, again, force of friction must be greater than the force of friction maximum. We're sticking with the coefficient of friction of 0.4. Let's draw the top block. I'm going to push with an unknown force P. I got a force of friction, which in order to make it slip, this is what we're looking for. We're looking for how much force does it take to make it slip. So in this case, if I'm assuming slip again, then I know the force of friction is going to be equal to mu normal, or 8 pounds. So let's plug that into our force equation. Sum of the forces X is equal to mass times acceleration in the X. P minus the force of friction is equal to 20 pounds divided by 32.2 acceleration. Now I have two equations, or I have two unknowns in this equation, so I can't really resolve that quite yet. So let's look at the bottom block. The bottom block is basically the same as what we did before. If I assume slip, then the force of friction here is 8 pounds. Again, this one's going to be equal to 0, and I can solve for the acceleration of the bottom block is 5.52. If I plug that back into this equation, I can find that the force required for it actually to slip over the top of the block, or for the top, is really 11.2 pounds. So that's really our answer. 11.2 pounds is enough to make it slip over the top. Now, if there was a secondary kinetic coefficient of friction, then the answers would, or the accelerations might change a little bit now because we have a different coefficients of friction. But just to get it to slip, just to get it to begin moving over the top, we need 11.2 pounds. I'd also like to set up these two homework problems for you. And I demoed this in the video a little bit, but in this first problem, we're pushing on the bottom block. I've already drawn the free body diagram, so I hope that you know kind of how to set that up. But let's just redo the top block. The top block moves forward as a result of the force of friction that happens between the two blocks. There's a weight, a normal force, and it results in a mass times acceleration going forward. Obviously, that means it's moving in the positive direction going forward. And the only thing that moves it in that direction is the force of friction. All right, and the cart down here is the same, similar kind of thing, where I'm pulling on the cart. The box goes with it. If it doesn't slip, then obviously the box goes forward. But if it does slip, the box still goes forward. In other words, it may go backwards relative to the cart, but the actual direction of the box is still forward. So if we draw the free body diagram of the box, it has a force of friction that moves it forward. It has a weight, a normal force, and it has a mass times acceleration moving it forward caused by this force of friction. So, and this is going to be the free body diagram regardless of whether it is slipping or not slipping. If it's slipping, then of course the force of friction is going to be equal to mu normal. If it's not slipping, then the force of friction is just a force, and whatever that force is, it causes that mass times acceleration in that direction. So again, it moves forward in a positive direction. The cart will have a similar kind of situation as the block above. You're going to pull it this way with that force P, or force F, and it has the normal force of A and the force of friction of A resisting, or force of friction and the normal force of A, which are transferred equal opposite. So again, this illustrates an extremely important concept that we carry over from statics, and that is wherever you have two bodies interacting or touching, the forces, whether they be friction forces or normal forces or any other kind of forces, the forces transfer equal opposite from one body to the other.